As you can see, we're going to take a look at finding the volume of solids. This is our third day in looking at volumes of solids. We've looked at finding the volume of solids in terms of x and y, and we've looked at solids that have a hole, and we've looked at solids that don't have a hole. The only axes that we have revolved our solids around so far are the x and y axis. In this video, we're going to take a look at how to find the volume of solids if we revolve the region around either a vertical or horizontal axis that is not the x-axis. This is on page 7 in your packet if you're in my class, and you can take notes there. Let's take a look at first at the keys to success. These are also printed in your packet. First of all, sketch the graph. That gives us the opportunity to look at the region and see what we're trying to find the volume of. Secondly, you're going to have to decide whether or not that solid, when you revolve it, has a hole or not, because that's going to decide if you need one radius or two radii. It's important, number 3, to draw the representative radii so that you can see um, the length or determine the length of that segment, and that's going to be even more important when you're revolving around horizontal or vertical axis. And then, of course, if there is a hole, you identify the big radius as well as the little radius, and that could also be r of y, big R of y and little r of y, depending on what you're revolving about. Number 5 is very important. When you're revolving around the x-axis or a horizontal axis, you integrate in terms of x. So again, I want to highlight that around the x-axis or a horizontal axis. In other words, if the axis is parallel to the x-axis, you are in terms of x. And I don't know why I don't have a number 6, but likewise, if you're revolving around the y-axis or a vertical axis, you are in terms of y. So you may want to add that to your notes. All right, let's take a look at the first example. And let's read carefully. We're finding the volume. We're going to form a solid. We're going to revolve, so we know that that's going to make circles, but this time we're going to revolve around the line y equal to 5. We're not going to revolve around the x or the y axis. All right, so first of all, I noticed that my equation or my function, it may turn out to be a function, is not in terms of x. So the first thing I'm going to do is get that equation in terms of x. So in doing that, I'm going to square both sides, and that'll give me x squared is equal to negative 1 plus y. I'm going to add 1 to both sides, so I get y equal to x squared plus 1. Now, I've mentioned this in class. Notice that graphically, this is a parabola, but if you go back up to your original equation, you're only, excuse me, you're only looking for the positive side of that parabola. So x squared plus 1 is a parabola that has a vertex at at y equal to 1, and we only want the positive side, so we have a graph that looks something like that. X equal to 0 is the x-axis, so we're going to have that region right there. And then y equal to 5, I'm just going to put it here. So the region that we're revolving is this region right here, and there's the 5. Now it says we're revolving around the line y equal to 5. So this is the line we're going to be revolving around. It is a horizontal axis. It's parallel to the x-axis. So we will be in terms of x. Very important to pay attention to. All right, I'm going to erase a little bit of this work here because I'm going to attempt to draw the reflection. Now it's actually going to go into my equation, so you'll have to bear with me. If we revolve around the line y equal to 5, then the reflection that we get would be something like that, and that solid's going to look something like that. Please forgive my attempt at trying to draw three-dimensionally. All right, so I'm going to go ahead and set up my integral. Oh, sorry, let's back up a little bit. This region is completely flush. It touches completely the axis of revolution. Therefore, in this case, there is no hole. Very important to identify. So Instead of having a big R and a little r, I'm only going to need little r of x. I'm going to go ahead and set up my integral. I know that I'm in terms of x. I know that I'm making circles, so I'm going to have pi, the integral, we'll figure out from and to in just a second, and I'm going to be in terms of x. Now the next part, very important. Write down what you hear me say. I may not write it down. The axis of revolution, the radius of our circles always travels from the axis of revolution to the outer curve. So the axis of revolution in this case is y equal to 5. So I'm going to start here, and the radius travels to the curve. So this is one representative radius. That is the length of the radius that I'm trying to represent. Remember, the radii vary as we move along. Also remember that when you're finding the length of that segment, you're going to find the high y value minus the low y value. Or you can think of it like when we did area. In this case, it would be the top bounding curve minus the bottom bounding curve. So in this case, the top bounding curve is 5. That's where the where the endpoint of the radius touches. So the length of this radius is 5 minus, again, top minus bottom. You're simply finding length, this value right here. Now that value is touching the curve. So we need the y value from the curve. Now remember, we're in terms of x. Even though they gave us the equation in terms of y, we are in terms of x. So that y value is generated by using the curve x squared plus 1. So the length of my radius is top minus bottom. Again, the top touches 5, the bottom touches the curve, and the curve is x squared plus 1. So my little r, my radius representative, is 5 minus x squared plus 1, and then I'm going to have to square that. I am in terms of x, so I'm going to go from left to right. So the leftmost x value here is 0. Now the rightmost x value, I need to know, this is the point of intersection, I need to know that x value. To find that, I'm going to figure out where my equation is equal to 5. So I'm going to set 5, just finding point of intersection, equal to x squared plus 1. Subtract 1 from both sides, you get x squared equal to 4. Take the square root of both sides, and you get x equal to plus or minus 2. Clearly this is positive 2, so we're going to go from 0 to 2. Now when you simplify that, I'm not going to do the integration, you can do that yourself, but when you simplify that, the first thing you want to do is to drop those parentheses and combine like terms. So you would have negative x squared, 5 minus 1 is 4. And now from here you can do simple integration and then sub and solve with the fundamental theorem of calculus part 1. Alright, so that's around a horizontal axis, and it is in terms of x. All right, let's take a look at a second example. This time we are still finding volume, so nothing's changing there. We are revolving, so we're making circles around the line y equal to 1. That's a horizontal axis. So now this time, notice I have two functions. I have y equal to the square root of x, which looks something like that, and y equal to x squared, which looks something like that. So the region that we're revolving is this region right here. We're revolving it around the line y equal to 1, which is where these two functions happen to intersect. We can prove that by setting them equal to each other. So I have the square root of x equal to x squared. To get rid of the radical, I'm going to square both sides. I'm going to x equal to x to the 4th. I'm going to get that equal to 0, so I have x to the 4th minus x equal to 0. I'm going to factor out x, and I get x times x cubed minus 1. So I get x equal to 0 and x equal to 1. So the point of intersection over here is 1. And when I substitute that into either of the equations, I get an output or a y value of 1, so this is the 0.11. We're revolving around the line y equal to 1, and you want to sketch that axis of revolution. This is parallel to the x-axis, so we are in terms of x. Now, since this curve, since the region that we're trying to revolve is not flush, it doesn't completely touch the axis of revolution. As you can see, I'm going to put this in and then I'll erase it. There's clearly space in here, so there's going to be a hole. Oops, that kind of erased part of the curve. Oh, making a mess here. So there's going to be a curve, a hole that we have to account for. So there's going to be a big R and a little r. So I'm going to need a big R of x and a little r of x. Let's start with little r of x. Little r of x, again, write this down, listen to it, play it over and over and over again. Little r of x is always from the axis of revolution. So my axis of revolution, dot some more of that in there. The axis of revolution is occurring at y equal to 1. So from the axis of revolution to the inside curve, that's the little radius. Now remember, top minus bottom. The top of this radius hits a y value of 1. The bottom of the radius hits the square root function. So the length of that radius, top minus bottom, is 1 minus the square root of x. Big R travels from the axis of revolution to the outer curve. To find the length of that radius, you subtract the endpoints. So the top endpoint is hitting 1. The lower endpoint, or the bottom endpoint, is hitting x squared. So it's top minus bottom. That's our big R and our little r. So our integration is going to be pi, starting at x value of 0, stopping at 1, big R of x, 1 minus x squared, minus little r of x, 1 minus the square root of x squared, dx. Now, when you do the integration, which I'm not going to complete, make sure that you do some cleaning up first. So, for example, square this binomial out, and then combine any like terms, and then do your integration term by term using the power rule to make it simple for yourself, and then do the substitution. Now I want to take a quick look back to make sure that I squared the r on the first example. Sometimes I overlooked doing that. Yes, I did, even though I know I'm supposed to. But you know what I see? In the first example, I combined these like terms, but I did drop off the square. So be careful. That is a common mistake. I know that I do that when I'm not paying attention. So make sure that you don't forget that when you're combining like terms. Glad I went back to look at that. All right, let's look at one more example, or I might have two more. Let's see. I want to look at this work one more time. All right, let's take a look at problem number 3. Notice this time we are finding volume revolved around x equal to 4, which is a vertical line, which is parallel to the y-axis, so we will be in terms of y. We have the same I think we have the exact same equations as we had in the first example. Yep. So we're going to take the same region, but we're going to revolve it around a different line, the line x equal to 4. Give me a second here. I want to find my page extender. Okay, so let me give myself a little more paper here. Not that much. Okay, so we said earlier that this was y equal to x squared plus 1, and we only want the right side, so x squared plus 1 looks something like that. We have the line y equal to 5, which is my axis of revolution. We have x equal to 0, so this is the region that's going to get revolved, and it's getting revolved around the line x equal to 4. Now we already, I think we established that, let's see, this is 0. What was the other? Was it 2? Yeah. So I think we already established that this point of intersection here is 1, 2. No, that can't be right. 2, 5. Sorry. Sorry, it's early. Bear with me here. 2, 5. Okay, back in the ball game. So x equal to 4. Here's 3. Here's 4. Is the vertical line. This is our axis of revolution. I think I said earlier that this was the axis of revolution. Sorry about that. The axis of revolution is x equal to 4. This is what we're going to revolve the region about. Now, clearly, there's a lot of space in between x equal to 4 and the region itself. So there's going to be a hole here. So we're going to have a little r of y, and we're going to have a big R of y. So let's figure that out. Let me erase that little. Okay, so little r of y, keep hearing this, write it down, think about it, is the distance from the axis of revolution to the inside curve. So it's the length of that segment. So it's the rightmost point. The rightmost point is hitting 4 minus, in this case, since we're in terms of y, it's going to be the right endpoint minus the left endpoint. The left endpoint is sitting on the curve, but we have to be in terms of y. So it's going to be 4 minus the square root of -1 plus y. Big R of y travels from the axis of revolution, which is x equal to 4, to the outer bounding curve, which in this case is the y-axis. Now notice, no matter where you draw that radius, the length of that radius is always going to be 4, because you're always hitting the y-axis. So that makes it a little easier. So we have our big R of y. So here is big R of y, a representative. Here's little r of y. All right, let's set up our integration. Pi out front because we're making circles. Now our bounds, be very, very careful. We're in terms of y, so the lowest y value is 1. The highest y value is 5. Little r of y is 4 minus the square root of -1 plus y, and that's squared. Big R of y minus little r of y, that's 4, don't forget to square it, dy. So this is big R of y minus little r of y. Again, some pointers when you are going to do the integration, which you should be doing. You're going to square this binomial out first, square the 4, combine like terms, and then the integration will not be too bad. All right, let's look at one more example. And by the way, if you notice, if you find any mistakes or whatever, you can email me and I'll try to fix those or put a note in the video. All right, let's take a look at finally at number 4. We're finding the volume of a solid. So we're doing volume again. We're revolving and making circles. X equal to 5. We have a vertical axis again. So we will be in terms of y, because a vertical axis is parallel to the y-axis. Now we have the equation x equal e to the y. So we need to get y by itself in order to, for our graphing purposes, even though we are going to be in terms of y. So to do that, we're going to take the ln of both sides to get that y down on the right-hand side is equal to y ln of e using a log property. The ln of e is 1, so we have y equal ln of x. Now that was just for our graphing purposes. We know already that the graph of ln of x goes through the point 1, 0 and does something like that. That takes care of that equation. Y equal to 0 is the x-axis, so that takes care of that. And then we're going to stop at x equal to 5. So this is the region that we're revolving. We're revolving it around the line x equal to 5. This is my axis of revolution. Notice that the region that we're revolving, which is right here, is completely flush, completely touches. There's no space between the region and the axis of revolution, so there will be no hole. And so we will only have a little r of y. Little r of y, the radius. I'm going to draw in my representative radius. Always start from the axis of revolution. So the axis of revolution is here, and it travels to the curve, which is here. That is a representative radius. I need the length of that. The length of that radius will be found by taking the rightmost endpoint minus the leftmost endpoint. The rightmost endpoint, as you can see, here's the right, here's the left. The rightmost endpoint is 5. The leftmost endpoint is the curve itself, but we have to be in terms of y, so that's e to the y. All right, let's set up our integral. Pi out front because we're making circles. We're in terms of y, so the lowest y value that we see is a y value 0. The highest y value we have not found yet. We'll do that in just a second. Let's go ahead and get our radius, 5 minus e to the y, don't forget to square it, dy. Now, we need to find our upper bound y, so we need to figure out, this is the x value of 5, so I'm just going to take and substitute that into the easy equation, which is right here. So y is equal to the ln of 5, which is perfectly fine because if you notice, we're going to be integrating a function that involves e, so that's probably going to take care of that ln 5. Again, you would square this binomial, so I'm going to take that actually one little step further. So that would give me pi from 0 to the ln of 5 is equal, or integration of 25 minus 10 e to the y plus e to the 2y dy. Now this term is simply integrated by reversing the power rule. This term, when you find the antiderivative of e to the y, you get e to the y. This term is going to either require formal or informal u substitution. In other words, you're going to have to compensate for that coefficient of 2 with a 1/2. Some of you are more experienced at doing that in your head, and some of you still actually need to do the u substitution. If you have trouble integrating that, come and see me. You can take a look at your textbook, which actually works the problems all the way out and does some examples of the integration all the way through. And then you can see if you're in my class and that the assignment will be page 463, 11C, 11D, 12C, 12D.